Alright, we're going to look at tests about a population mean instead of population proportion. So a classic rock radio station claims to play an average of 50 minutes of music every hour. However, we don't believe that. To investigate their claim, we randomly selected 12 different hours during the next week and record what the radio station plays in each of the 12 hours. Here are the number of minutes of music in each of these hours. So here are the number of minutes per hour that the company is playing of music. So we don't even have stats, we have our raw data. So first thing we have to do is type it in our list on the 84, or if you're using the TI Nspire, you need to put it in your list and spreadsheets. So we have to put in our data. Then we start our phantom. Notice there is no alpha given, so we're going to use alpha of 0.05. We'll get to that later. So P, the parameter, is mu, because we're talking about mean, is the true mean number of minutes of music played on a classic radio station per hour. It's very specific, but that's what it has to be. Our null is that mu equals 50, because that's what the radio station claims, and it's always an equality. And we're saying it's different. We're not saying that it's more or less, it's just different. So it's not equal to. That's the alternate hypothesis. Now our assumptions for our mean, it's got to be random. 10% rule, clearly 12 hours is less than 10% of all hours the radio station plays music. And then, well, we only have 12 things of data. So that's not 30, so by the central limit theorem we can't do that. So what we do is what we did last chapter, create a box plot and a normal probability plot. Again, if you're using the Nspire, Control I, go to Data and Statistics, click to add variable and X. Of course, that gets you the dot plot. Then you go to Menu, Plot Type, Box Plot. And what are we looking for the box plot? We're looking to see there's no outliers, there's no numbers by themselves, so we're okay. We also want to see the normal probability plot to see if our population data is normal. And it fits the linear pattern pretty well. There may be kind of a pattern here, but it's pretty linear, so we're going to say the population is normal. We need to label it 44 to 53, and we have our z-scores here. We're using the 84. We put in our data. We have to go to second y equals, do the plot, and we want to turn it on if it's not on. First we'll do the box plot. We hit graph. Oh, that's not what we want, so zoom, and number 9, zoom stat. There we go, we got a box plot, no outliers. We kind of have to see what those numbers are, so the best way to do it is trace 44 up to 53. So again, same type of thing. We need to scale our x-axis here. We also need a normal probability plot. So second y equals, go to the plot again. And now we want to go to the last one, which is the normal probability plot. And just hit graph. Again, zoom, stat, number 9. Again, pretty linear. There's kind of a pattern, but for the most part it's linear, so we're going to say that our population is normal. So I have my box plot and my normal probability plot. There's no outliers, population is normal. N, one sample t-test. Test statistic. If we go back to 9.2, our test statistic is the statistic minus the parameter. So our statistic is x bar, the parameter is mu, so x bar minus mu, over the standard deviation of the statistic, well, standard deviation of the statistic is x bar here, so we're going to use s sub x and n. So we get this. We get a t-score of negative 2.5674. Again, we got the mean because we had to find the mean of this data. Now on the 84, it didn't quite show it. So, stat, calc, one variable stats, and it gives you X bar, and S, 2.8109. So we have what we need there. Whereas the Inspire gives it to you here. Here's the mean, here's the standard deviation, gives it right on the normal probability plot. So now we need to do 2 times the probability that t is less than that. We're doing less than because even though it's two-tailed, it is two-tailed, this is negative, so we do less than. So negative 2.56, this would be 2.56, we need to do both, so that's why it's 2 times that. And we still have a low p-value, 0.026171. We compare that to alpha, which is 0.05. It is less than alpha, so we reject the null. We have sufficient evidence to reject the null, ergo, we can support the claim that the true mean number of minutes of music played on a classic radio station per hour is not 50 minutes as advertised, based on our sample at alpha equals 0.05. So basically, we can support the alternate hypothesis was it's not 50 minutes. If you could probably guess, it's less than 50 minutes, because if you look at all these, most of them are less than 50. Now, if we were to do a confidence interval, again, if we do our tests and go to t-interval, use data, confidence level 95, that looks all fine, calculate, there's our lower bound and upper bound, gives us X bar and S. If we're doing this here, we need a new page, Control I, a calculator page, menu, statistics, confidence intervals, t-interval from data, I label it X, gives me the same numbers. So my confidence interval is 46.1307 to 49.7027. Well, mu is not in there, so we reject the null. So it's just another confirmation that we were doing it the right way. We have another problem here. The mean height of American males is 69.5 inches. Heights of the 44 male U.S. presidents, Washington through Trump, have a mean of 70.88 and a standard deviation of 2.77 inches. Treating the 44 presidents as the SRS, determine if there's evidence to suggest that presidents are taller than the average American male. Alpha is 0.05. So here, mu is the mean height of all U.S. presidents. Our null is that mu is 69.5 as advertised. Our alternate is that mu should be greater than 69.5 because we're trying to see if they're taller. Assumptions, random. It says it's a SRS. They kind of cheated, but they told us that. Clearly 44 presidents is less than 10% of all American men. And n equals 44, which is greater than 30, so the population is normal. It is a one-sample t-test. And now I'll show you how to do this on the calculator without doing all the work. So if you have the Inspire, menu, statistics, stat tests, and t-test. We don't have data, we have stats. So our mu was 69.5. X bar was 70.88. Standard deviation 2.77. N is 44. And we want to see if mu is actually greater than that. So we get a t-value, we get a t-score, a p-value, and that's what we need. We can do that on the 84 just the same, stat. over to tests, t-test, from stats, x bar we said was 70.88, oh, the mu was 69.5, again 69.5, and standard deviation was 2.77. N 44, and we want to see if mu is greater than mu naught, so it is this last one. There's our p-value, that's scientific notation, so it is the same as what we got before, and our t-score. So t-score is 3.305, p-value 0.00962, obviously that's less than 0.05, so we reject the null. We have sufficient evidence to reject the null, ergo we can support the claim that the mean height of all US presidents is greater than the national average based on our sample at alpha equals 0.05. What is a type 1 error in this situation? Well, type 1 is where we reject the null and we shouldn't have. So we concluded the mean height of the presidents is taller than the average American adult, but they are not. So that could have been the error that we would have done because we rejected the null. A type 2 error is when we failed to reject and we should have. So we concluded the mean height of the presidents is not taller than the average American adult, but they actually are taller. That would be a type 2 error. So that is one sample t-tests.